Hey everyone! In this video, I will be doing an overview of a SIMULINK model of a variable reluctance motor. It's also known as a switched reluctance motor. So we will go through and explain each block in this SIMULINK model and talk about the different inputs and outputs and finally show the results of the simulation through the graphs on this scope right here. You can find this model by simply going on the MATLAB website and just searching switched reluctance motor. You can also go into MATLAB and over here just type in the command window power underscore switched reluctance motor, hit enter, and the simulation should come up. That simulation does include 3 different phases of a switched reluctance motor, but in this video we will only be talking about a 3-phase 6-4 switched reluctance motor. So to get started, we have here the 6-4 motor, which is 6 stator winding and 4 rotor poles. So essentially it's a 3-phase motor. As you can see here, A is 1 phase, B is 2nd phase, and C is the 3rd phase. So here we have the outputs coming out from the motor. So we have the flux, current, torque, and speed. So we have one output for each phase, and we end up with 3 signals for each of these variables. So the first block that I want to talk about is the position sensor over here. So the position sensor has 3 inputs, 2 of them being the turn on and the turn off angle. These you can easily adjust by just double clicking on the box and just putting in the value that you want in here. The third input is the speed or the position that's coming as an output from the motor. So here, let's double click on the position sensor so we can have a better look at what's going on. So over here we have the position, which is the output from the motor, which then gets converted into degrees, and we use the modulus function to compare it to the turn on and the turn off angle, so that if the position of the rotor does indeed fall between the turn on and turn off angle, then that means that the rotor needs to be changed so that the phase is aligned and the AND gate outputs a binary 1. Otherwise, it will output a 0, so that means that the position does not fall within the turn on and the turn off angle, and we don't want the rotor to rotate. Now, if we go back and look at the model, we can see that the output of the AND gate gets multiplied by the reference current, which in this case is 200 amps. And if the output is 0, then a 0 goes through the next block and nothing happens. If the output is a 1, then the reference current goes through to the next block, which takes the input of the current from the motor and subtracts it from the reference current. So it takes the current from over here, that's what this line is, and that current gets subtracted from the reference current. After we subtract the current, it goes into the hysteresis band right over here. So the hysteresis band kind of acts as a safety switch so that we don't send in high currents to excite the motor and then burn it out. So here we have limits of the band, which are set to +10 and -10. So that limits the stator output current to be between 190 and 210 amps. The band then outputs a square wave for each phase, which goes into this converter in order to excite the motor. In addition to the pulse signal from the hysteresis band, the converter takes in a 240 volt voltage source. It's in DC, and if we take a closer look at the converter, here we can see that we have 3 converters, one for each phase, and each of them take the voltage sources as the input in addition to the pulse from the hysteresis band. Now, if we double click one more time at one of the converters, we can see what's happening inside the circuit. So here we have 2 IGBTs, one right here and another one right here, and these 2 IGBTs output positive voltage depending on the pulse signal. We also have 2 freewheeling diodes that output negative voltage and return the stored energy back to the power source. The diodes also reduce any ripple that could be caused in the torque or the current as a result of the sudden stop in the flow of current through the inductor. So essentially what happens is when you excite a phase so that it rotates and gets aligned, then you suddenly stop the flow of current so that it doesn't move any further than the turn-off angle. So that period where the current is suddenly cut off from the inductor is the freewheeling period, and it can cause ripple in the voltage and as a result in the torque and the current. And basically what these diodes do is that they help reduce that and they return the power back to the power source. So if we zoom out again, we can see here. So here's the output of the converter, which is the voltage. So these are the positive or negative voltage that gets supplied directly to the stator windings, which then supply current to flow through the phase windings in the motor and thus rotate that phase until the turn-off angle is reached and the phase is aligned. Alright, so let's run the simulation and take a look at the output signals. So if we just click play, we can double click on the scope to get the output signal. Now this looks a little messy, but so you can see here we have 4 graphs: flux, current, torque, and speed. So let's zoom in a little bit. So this is the time varying flux, and we'll get a closer look at it in a second, but I just want you to see here, this is the ripple over here, and over here is the ripple in the current and the torque that I was talking about earlier. So we have the different colors for each phase. So that might be too much. Okay, so purple we have for phase A, blue for phase B, and yellow for phase C. So let's try zooming in one more time. Okay, so now we can clearly see how this is a linear flux and time varying. Over here we can see how the current, so once the current is high for one phase, the other two are either 0 or really low. Also, one thing to notice is as we zoom out, you notice over here the current kind of goes down and the ripple kind of goes away. So that happens after the speed reaches about 3000 RPM. So at that point, the motor is excited is not current controlled anymore, because at lower speeds, since speeds above 3000 RPM, stator currents do not reach the reference current anymore, and that's kind of why you see it decrease. So you see here it's about 100, 90, 80, and of course it doesn't exceed 200, because that's a reference current. So over here, after the speed reaches 3000 RPM, the current does not need to be controlled anymore, and the motor becomes excited by the voltage only, and that's called the voltage fed method, instead of current control, where we need the hysteresis band to control the current. Yeah. Here's a simulation one more time, and we get the same results. Alright, and that's it for the simulation. I hope you enjoyed it, and I hope it helps. Thank you.